Right, can everyone hear me?
Yes.
Excellent, right. I'll try and zip through this quickly. So, just firstly, quick introductions. My name's Alex Benet. I'm a senior virtualization engineer with Linaro. I mostly work on QEMU, and the bit of QEMU I work on the most is the TCG part, which is what's used for emulation. I've been known to do a bit of KVM stuff as well. You can find me on the Linaro IRC channels as AJB Linaro, and on the QEMU IRC channel as ST Squad. Just a couple of notes on the code in this presentation. All the analysis code is written in Python. Where you see these double chevron things, they're just no web inclusion. So it's just so I can run the code and make sure it works, but I've not included it in the presentation because it's generally boilerplate stuff. But if you want the source code for these slides, give us a shout and I can send them to you. So, why do we want to use virtual machines for doing experiments on code? Well, the first reason is measurement. Measuring things on hardware can be quite hard. It generally involves attaching lots of wires. It will also depend on having the information that you want exposed by the hardware. And of course, everything in software is easy because you can just simply rebuild it and add what you need. The next reason is control. When you're running a machine in a virtual environment, you can completely control what that machine sees. So you can decide what hardware it sees, when it sees it. You can even freeze time, examine what's going on, and advance time at a speed that's helpful to you. You can even rewind time if you're being exceptionally clever. And the next reason is to aid analysis. So if you're using hardware tracing facilities, you've often got limited buffers in which you can trace. When you're doing things in software, you're basically limited by the size of your hard disk. So there are a number of example tools that exist in this space. Dynamo Rio is a BSD licensed toolkit. Intel PIN is their proprietary offering, and the venerable Valgrind also has a tools interface. However, one thing that all these tools have in common is they target user space programs. So what about QEMU? I mean, QEMU is an open source virtualizer. Most people have come across QEMU using it for KVM, but in this case, what we're interested in is in its emulation abilities. So QEMU supports 21 guest architectures, and it can run code for all of those guest architectures on any of its major supported architectures. I think there's about 7 backends, including ARM. There are 2 modes in which this emulation runs. The first is Linux user emulation. So this is for running Linux user space apps, and it's a pretty fast way of running them. And the reason it's fast is because it only has to concentrate on translating the user mode part of the code. When the user mode code makes a system call, QEMU takes that system call, munges the parameters, and then passes it down to the host system. The next mode that you can run QEMU in is what's known as full system emulation. So here we're emulating a whole machine, including hardware with peripherals, and then you're running in that machine a guest kernel, and the guest kernel has its own user space applications. This is generally quite a lot slower than running in user mode because we also have to make sure that we're emulating things like the MMU properly. So let's look at some simple tracing that we can do. So the log subsystem of QEMU was basically designed as a developer tool. So this is the sort of thing that QEMU developers use, but you can do some interesting stuff with it. So here we've got an example trace. So the binary is one of our test binaries that we run just to verify that the TCG is working properly, and it simply computes a SHA-1. It's a nice simple binary, but it's a good test case to make sure all your logic instructions are doing what you expect. So the little d, minus d CPU is telling it to dump the CPU state, and the capital D is telling it what file we want it to go into. If we have a look at the trace file, you'll see something like this. So here we're dumping the complete state of the register file, so all the general purpose registers, as well as a couple of bits about the processor state. You can extend this trace as well to include FPU information and SIMD information if you want. So let's look at what we've got in this trace file we've just generated. Now the size is a little bit of a lie because I'm running on ZFS here, so it's reporting a smaller size than the actual file. I think the total trace file, according to LS, is about 0.5 megabyte for this run. And you can see we've collected 799 program counters. So let's do a little bit of analysis on those data points. So the first thing we need to do is we need to get the data into something to do the analysis with. So I'm using Python here, and I'm particularly using the NumPy Python package, which is a package for dealing with large arrays of data and doing scientific analysis on it. So the first bit here was simply running a regular expression and collecting all the program counters. Then once we've got them in our NumPy array, we can start doing some basic analysis. So I can see where the bottom program counter is and where the top program counter is, get an idea of where where this code is running in the memory map. And we can then start to think about doing some simple statistical analysis. So the bin count function here basically adds up the number of times a program counter appears and counts how many times each program counter has appeared. So you can see here, most frequent program counter in this run was 41B600, 12 times it's been seen. But this is a little bit dry. Sometimes it makes sense to visualize this information. So we can, what I'm doing here is I'm preparing the data to plot it in a 2D heat map. So the first bit, I'm just simply making sure everything's a nice number of, even number of pages around. I'm doing a reduction, so I'm actually making each bucket cover about 4 instructions. This is just to reduce the total number of data points that I have to plot in the graph. And then finally, I'm formatting this in a nice 2D grid. And then I pass it on to NumPy's matplotlib to plot it, and that's a trivial piece of code. And you get a result that looks something like this. Now, the contrast isn't particularly good on the projection, but you can see the little white spots, and that's where the hot code is, and then everything gets progressively darker for the less hot code. But there's something that's a bit wrong with this. The execution count of 14 on the highest PC is not particularly high, and so we need to have a little diversion into the way the TCG runs. So this is a basic example of the TCG run loop. So the way QEMU works is when we get to a particular program counter, we look up in our translation cache to see if we've got a translated block to run it. If we haven't, we need to generate that block. And then we insert it into our translated buffer, and then come from our run loop and jump into the translated code buffer, and then return. So what we've actually done is we've measured code coverage for the program, but we haven't actually measured how frequently every single block is called, and that's because we do a thing called block chaining. So the coming out into the run loop is fairly expensive, and most of the time it's unnecessary. And what we do is when we translate a new block and we find the 2 blocks jump from one to the other, we patch it directly, so we jump straight from block to block to block. So we reduce the number of times we come out into our run loop, which is where the debugging print comes in. Fortunately, the block chaining mechanism has been something that's not been without bugs in the past, so we have a useful flag that allows us to turn it off, no chain. And now you can see we've got a lot more useful data, 36 meg of trace data and nearly 1 million program counters. So we can do some analysis on that, and that's more like it. We're seeing the program counter 41C 400, 64,000 hits. That's more what we're looking for. So we can plot that in a heat map, and it doesn't actually look particularly pretty, but it does show you the white points, the most executed code. It actually works if we use a log scale, we get a little bit more resolution, which there we go, hopefully will show up on the projector. But these program counters aren't exactly every single program counter that's being executed. They're actually the first program counter of each executed translated block. So what we could do is we could turn on single stepping in QEMU, and single stepping just limits the number of instructions to each translated block that we run to a single instruction, and we can collect our log that way, and you will get space because the file is huge. But actually, you probably don't need this level of detail because each block that we translate is a whole group of instructions that's going to run one after another, and it's only when we come to a decision point where we've got a conditional branch that we stop our translation. So in terms of working out where your code is going, that should be enough. There's one other thing we can do, though, if we're particularly interested in areas of the code, is use a feature called defilter. So all defilter does is it applies a filter to the program counter and limits the output to the log file if the program counter isn't in the range that we specified. So the addresses here I've picked are actually the start and end of the core SHA-1 routines themselves, because I'm really not interested in getting any execution profile going through glibc for printing the result at the end. So we can plot that in a lot more compact heat map, and you can see exactly where the hot points in the code are and where the next hottest bits. So just to summarize the log options you've got, so dCPU will dump the state of the CPU. It's quick. You get relatively small trace files, but what you're really covering here is translation. So it's good coverage for every piece of code that has been executed, because we have to translate it at least once, but it won't tell you how often it's executed. If we want to see how often it's executed, we need to turn on the no chain option. And if you really want to massacre your hard disk, you can turn on single step and get huge trace files. But that's just the built-in debugging support. QEMU also has a trace facility and an internal tracepoint API. So the tracepoint API is fairly simple, but it allows you to export a lot of interesting data. So the way you add an additional tracepoint to QEMU is you simply have to define a prototype for the tracepoint, which the type of information that you've got, and a little format string. Format string is actually used by the tools, so when it renders the data afterwards, and then you just make a call to the tracepoint in the code. Now, tracepoints are fairly lightweight because it's a very well predicted branch, and if the tracepoint's not enabled, it will just run over it very quickly. One advantage the tracepoint API has is you can have multiple different types of output. So the default is plain text, and it will use the existing logging system and output a text rendition of the tracepoint. We also have what we call simple, which is basically a binary logging file, but that's a lot better if you want to have compact data. Dtrace and ftrace, these are probably not things you're going to use if you're just analyzing code in the emulator, but they are quite useful for the KVM users, because you can then run analysis on trace points in QEMU and correlate them with trace points in the kernel. And finally, we've got user space tracing and syslog are also useful in some cases. So why do we want to use the trace files? Well, trace files are a lot more compact than the debug logging, so it's going to be faster at the out point. Also, you've got a lot more interesting trace points. We've got trace points in a lot of the major drivers, as well as we've got integration into the code generator itself. So if we were going to do the previous experiment but using trace points instead, this is the example. So again, I have to enable no chain, but instead of tracing the CPU state, I'm enabling the exec_tb trace point. So that is a trace point that runs before we execute every translation block. As you can see, the final file is a lot smaller. But let's look at some of the more interesting trace points. So this is an example of a trace point that will trace all memory accesses run by the program. So it's called guess mem before exec, and it will basically inserts a helper on every single load and store in the program, and then logs that to the tracing facility. So if we have just a look at the example trace file we get, you can see for every trace point we've got a timestamp. All trace points have a timestamp associated with them. And we're tracing the program, the PID, what CPU it's running on, and then the virtual address that we've just done an access to. And the info at the end is a little encoded bit of information that's holding the size of the access, whether it's big endian, little endian, that sort of stuff. So we can do some analysis on this. We can use the simple trace API. So in the QEMU source tree, there's a Python simple trace class, and we can build our own class, a mem analyzer based on that analyzer class. And all you need to do is you need to add a function for each trace point that you want to analyze. So all I'm doing here is for every guess mem trace point, I'm making a record of the address, and I'm keeping a track of what sizes are run. So if I do that analysis from the program I've just run, I can see exactly how many loads and stores it did in total, and a breakdown of the sizes of those various loads and stores. Another useful thing you can do with QEMU is you can do dynamic tracing. So when you're running in system emulation mode, you can use the man-machine monitor to interrogate the state of QEMU. And one of the things you can do is you can turn trace points on and off, and you can also turn the tracing file on and off. So the trace points I'm looking at here are the block driver trace points. So I'm looking at the number of bytes that are being written and read by QEMU's block driver. So what I've actually done is I'm going to run several, generate several trace files when I'm doing various different things. So here's the analyzer, pretty much the same as the guess mem analyzer, except all I'm doing is I'm summing up the total number of bytes that I've read and written. And the experiment that I've run is I've done a compile of the QEMU source code just after I've booted up, and I've set a new trace file. I did a make clean, set a new trace file, and then ran the compile again. So plotting that result, it's fairly simple code. I'll skip over it because it's not particularly interesting, but we get a nice graph like this. So this is exactly what we'd expect to see. In the cold case, we spend quite a lot of time reading stuff off the disk, and then when we recompile it with the hot cache, we don't read anything off the disk because it's already cached in RAM. There's a couple of things to mention about these sort of analyses. There's timing issues when you're doing stuff with TCG. So if your program is a straight run-through user space program, it doesn't really matter. But if you've got timers running and you've got or an interrupt handler, you need to be aware that the interrupt handler is going to run slower under emulation than it is on the real hardware. But we do have a solution for this. It's called iCount. The iCount basically, instead of reporting time as the wall clock time of the host system that you're running on, now reports time based on the number of guest instructions you've executed. Now, it's important to point out this isn't a cycle-accurate emulation of the guest instructions, but it does give you a deterministic way of running your code. So in this case, I think each instruction counts for 1 nanosecond of elapsed virtual time. I'll skip over this. All right, just want to quickly talk about some of the things that are in development. I'm running late. So reverse debugging. So this builds on our iCount infrastructure. So without iCount, assuming all other things are equal, you can get deterministic playback. So you can record a trace with iCount enabled, and then as long as you've enabled snapshotting on your disk, you run it again, you should get exactly the same execution because things will happen at exactly the same time as far as the guest is concerned. And building on that, there's the record replay ability. So this is currently a patch on list, and this extends our GDB stub to support the reverse execution primitives that GDB supports. So you can do funky things like crash a bug and then rewind 10 instructions and see exactly why you got there. Another area of development is plugins. So this is taking a bit more time. It's an RFC at the moment, but what we would like to do is support the ability to have more interesting experiments loaded as plugins into QEMU. But as with any plugin API, there's quite a lot of debate about exactly what the scope of that API should be and what sort of guarantees we make about API stability. So it's an area of active debate. I just want to mention our own work. So there's an epic in Jira called Vert252, and that's the QEMU tooling epic, and there's a number of things that we're looking at improving in the way that QEMU runs. So better memory logging. So the memory logging I pointed at before doesn't tell you anything about the values that were loaded and stored into memory. iCount for user mode. There are some complications in this because if you're doing user mode emulation, you're actually talking to the host system, so you'd have to take care with things like timers, but it could be potentially useful. Block execution counts. It's all very well counting up all the blocks that... I know, I started 15 minutes late. I'm not almost done. So instead of collecting all this data in a massive log file, QEMU would be quite capable of actually just counting the number of times each block is executed and dumping that. So in summary, why... Right. Why QEMU? It's cross-platform, so you can run a whole number of different guest architectures on any of our supported host architectures. The fact that it supports system emulation allows you to do more interesting experiments about the way things like kernels work. And it's also an open platform that's nice and open for hacking and experimenting. Tracing API, use the tracing API. It's better than using debug logs, and it's an area of active development. We haven't really got time for feedback, but please, if you're interested in running any sort of experiments in QEMU, come and grab me, not after this talk, but later in the week, and tell me what sort of things you'd like to run and what sort of things you'd like to find out about how your code works. Okay? Thank you very much.